Hello, Anand. I am Manisankar studying ECE in Japanese Institute of Technology. Now I am going to talk about the Poynting theorem and wave power, which is for the purpose of case study for the subject Electromagnetic Fields. Let us move to the topic Poynting theorem. With Maxwell's equation, we now have the tools necessary to derive Poynting's theorem, which will allow us to perform many useful calculations involving the direction of power flow in electromagnetic fields. We will begin with Faraday's law and we will take the dot product of H and H with both sides. Then the first equation is del into E is equal to del cross E is equal to minus dou B by dou T, and H dot product of this function, which will form the equation as minus H dot of dou B by dou T. Next we will start with Ampere's law and we'll take the dot product of E with both sides. Del into H, del cross H is equal to, which means we have here take Ampere's law. So del cross H, which will give the equation as dou D by dou T plus J. When we substitute it in the following equation, E dot del cross H. So in this del cross H, if we substitute this value, then we will get E dot dou D by dou T plus J. So now we have the equation for H dot del cross E and E dot del cross H. We can now apply the following mathematical identity to the left side of the equation. So this following equation we have here is del dot A cross B equal to B dot del cross A minus A dot del cross B. This is the format of the equation which we have to substitute here in the above equations. Okay, so when we substitute it, then we will get del dot E cross H. So we here have the common term as del and the different terms are E and H. So del dot E cross H is equal to minus H dot dou B by dou T minus E dot dou D by dou T plus J. By distributing the E across the right side gives del dot E cross H is equal to minus H dot dou B by dou T minus E dot dou D by dou T minus E dot J. So we separated this equation with E. Now let's concentrate on the first time on the right side. Applying a constitutive equation, we find H dot dou B by dou T is equal to H dot mu of dou H by dou T. This is the constitutive equation. Let's consider for a moment what the derivative of H2 would yield. Dou H square by dou T equal to dou of H dot H divided by dou T is equal to 2H into dou H by dou T. This is the derivative of H2 which we yield here. By dividing this equation with 2, we will get the answer as H dot dou H by dou T, which is equal to 1 by 2, which means dou of H dot H. Here this equation we have, which is divided by 2, and then we get the result as 1 by 2 into dou of H square by dou T. Because of H into H is equal to H square, the dot product of a vector with itself is the magnitude of vector squared. A similar analysis of the second term on the right side yields E dot dou E by dou T is equal to 1 by 2 of dou E dot E divided by dou T is equal to 1 by 2 of dou of E square by dou T. You can see here this equation is similar to this above equation. Already they say here a similar analysis of the second term on the right side yields. So this is for E, the term E, and this is for the term H. So we already yielded the two equations by substituting the above two equations in distributive equation. So we got for H and we got for E, so we have to substitute it in the above equation which we solved here. You can see del dot E cross H. In this equation, if we substitute these two equations, then we will get the answer as del dot E cross H is equal to minus 1 by 2 dou by dou T of mu H square plus epsilon E square minus E dot J. This is the equation when we substitute this both of the equation in the distributive equation, and then by taking a volume integral of both sides, then we will get volume integral del dot E cross H dV is equal to minus 1 by 2 dou by dou t of volume integral of mu h square plus epsilon e square into dv minus volume integral of E dot j dv. By applying Ohm's law, which we already know, J is equal to E to the right side, then we will get volume integral del dot E cross H into dv is equal to minus 1 by 2 dou by dou t volume integral of mu h square plus epsilon E square into dv minus volume integral of sigma E square dv. By applying the divergence theorem to the left side, we will give that will give closed integral surface integral E cross H dot ds is equal to minus dou by dou t volume integral of 1 by 2 mu h square plus epsilon E square dv minus volume integral sigma E square dv. So this is the equation which is in the integral form of Poynting's theorem. Each of the terms in this equation has a physical significance. Let's start with the left side. The factor E cross H, this term E cross H is called the Poynting vector, and it represents the direction in which energy is flowing. This is representing the direction in which energy is flowing. We represent it by variable s. So the E cross H we can represent it by the term variable s. Here you can see s is equal to E cross H. The Poynting vector can be used to determine the net power flowing out of an enclosed space. S will show the direction of power flow, which can be difficult to determine from E and H. Note that if the integral of S is positive, net power is leaving the region, while if the integral of S is negative, power is flowing into the space. So if S is positive, the power will leave from the region, and if power is negative, if S is negative, then the power will flow into the space. The first term on the right side represents the total energy stored with the enclosed surface. We can simplify this expression by making the following definition: omega is equal to 1 by 2 of mu h square plus epsilon e square. This is the term which we have second. So we have to substitute that equation as, we have to take that equation as this. You can see here mu h square plus epsilon e square. We have to take that as omega. Okay. So already we take E cross H as S. Now we take h square plus epsilon e square as omega. The first term in this expression represents the energy stored in the magnetic fields, such as in an inductor, and the second term represents the energy stored in the electric field, such as in a capacitor. In many cases, one of these terms will be zero, simplifying the calculation. Okay. This is, you can see here, this is a H, this is the representing the energy stored in the magnetic field, such as in an indicator. This represents the electric field in a capacitor. The second term on the right represents the energy being dissipated within the enclosed surface. This is the energy that is being converted from electromagnetic potential energy into heat energy, such as in a resistor. We represent this quantity by the variable PL, which is defined as sigma E square. So here in this equation we have sigma E square at last of this equation. So we here substituting PL for this sigma E square. So finally we got all the variables for substituting. So finally Poynting theorem can also be represented in the point form as del dot S plus dou omega by dou t is equal to minus PL. Here we have substituted all the terms which we represented above. S, omega, and then minus PL. That's all from my side. Thank you.